My name is Jonas Karlsson. I work here at Google, and I'm happy to introduce Mikael Ronstrom here, who's going to talk about cluster databases. And I'm especially happy that he's here talking about this because I kind of can blame myself for a little part of things which he's using inside his system, and kind of makes me a little bit proud that things are being used somewhere else than just being in a book somewhere. Mikael Ronstrom, he's from Sweden. He built the cluster database system, which is integrated in the MySQL Cluster. And this was a project we started many years ago, but not too many years ago. While I was a Ph.D. student, he was a Ph.D. student. And I think his idea is actually precursor his Ph.D. studies in database systems, which we worked on for Ture Risch in Sweden. And now he is an independent consultant at iClaustron. And he's still working for MySQL clusters, and I will give him the floor here.
Okay, thank you. So the talk today I'm planning to talk about is a little bit some new ideas about how you can use the technology from MySQL Cluster. So I call it a grid cluster, so you'll understand when the presentation is done where that word comes from. And it's actually not about databases, it's more about storage and handling larger sums of data than databases traditionally use. Before I do that, I can just sort of briefly talk a little bit about MySQL Cluster. So MySQL Cluster is a storage engine within MySQL, and you have a MySQL server, and it connects to other processes in the backend, which is the actual cluster. So the actual cluster is stored in nodes that we call NDB. So that's where the actual data is stored. So that means that the MySQL server is actually just a client to the NDB nodes. So that means that any number of MySQL servers can be clients to this data cluster. So that means that you can do an update in one MySQL server, and any other MySQL server will see that update. And this obviously means that there is transaction protocols, that distributed transaction protocols handling, and a lot of things like that. From the beginning, MySQL Cluster was a main memory database. And the reason of that was because this work originated from a company called Ericsson, which is in the telecom business. And in telecom, this was used mostly to keep track of where your mobiles are. And it's actually still at the moment keeping track of that. So it might very well be that if you have a mobile here, that it's kept track of by usage of MySQL Cluster. Because that's the type of system where it's fairly heavily used. So there are millions of users today that uses MySQL Cluster. The very first customer that we had was actually a broadband customer that developed this for a DNS and DHCP solution. And interestingly enough, that's the broadband operator that I have at home. So I actually was a partaker of the technology I developed very early on myself. So, first the outline of the presentation. So I'm going to talk a little bit about one of my pet applications, genealogy. So already from the very beginning, when I started my work on databases, I was very, very much interested in genealogy. So what I always wanted to do was to build sort of a database that was able to handle the genealogy application. But already from the very beginning, it was pretty obvious that when I started this work in 93, 94, or even earlier than that, that the kind of requirements that the genealogy application had was not something that was going to be around in the next, say, 10, 15 years. But 10, 15 years has gone by since that time, so we're actually getting very close now to being able to handle the technology for building a genealogy application. There are other things like email application. Well, I'm going to talk about the architecture of this extensibility and talk a little bit about the components of the architecture. So we'll start with the genealogy application. The base data for a genealogy application is all the historical documents that exist. And there are quite a few of them. And those historical documents have been microfilmed and they've been scanned into computers as well, so that they are stored in digital format. And there are literally billions of images, where every image is about 1 byte per image. That obviously varies dependent on the resolution you want to have and so forth. And I guess most of you are pretty have knowledge about mathematics, so you can probably calculate that that means petabytes. And it also means that, so there are petabytes of image data, but there is also terabytes and many terabytes of transcribed data. And the transcribed data means the data that you actually, when you take the image and you put it into text, that's the transcribed data. So these are the typical objects that you would find in a genealogy application. So it's the scanned objects that I refer to as the images. And then you have the transcribed objects, which is just trying to write down what the text is actually written on these documents. And then you have catalogs over all the images. And then you have the actual persons, the actual genealogy. That's the application objects. Link objects I'm going to show you in the next slide. And then name translation. If you take the name, for example, Maria, it probably has 17 different spellings in one particular area of a country. So you need to have ways to translate names in a way. This is probably too complex, but this is the conceptual schema. But the link object, the idea with the link object is that you have the image here, and then you find, for example, your great-great-grandfather in a book, and you're very interested, and you find his birth there. And then, of course, you're interested in to see whether anybody has transcribed any information so that you can actually read what it says, because try to read something from the 17th century, you will have a problem the first time. Maybe the 100th time you will have a little bit easier task. And if you're into things like image, trying to resolve an image, then it can be even difficult for the brain to resolve what's on the image. But that's another subject, so let's not go into that one. So anyway, the link object will show you what it actually says, or at least that's one view of what could be. So there could be actually several persons there that have different views on what it actually says there. And then you could use technologies like Amazon do with books, for example, that people have quality measures on different people, so that eventually the ones that pops up highest on the link object is the guys that has the highest quality according to the community. And in this case, the genealogy community. And, well, it's not so interesting. So if you look at the image data and think about building a system for image data, it's, if you have a system with petabytes of data and all these historical documents, there are really very few hotspots, because American people, they come from America, Swedish people come from Sweden. Well, American people probably comes from Sweden, some of them as well, but there are no particular historical documents that sort of give you more information about your ancestors than others. It's very much spread out. So that means that caching of image data doesn't really make that much sense. But obviously it makes sense to make sure that you can get to the data very quickly, so that you don't have to jump on the disk several times in order to find the data. So multi-petabyte storage, that means at the moment tens of thousands of hard disks and many hundred storage servers, a problem which I presume you're fairly familiar with at Google. And when I thought about this problem and thought about sort of how do I build a system with this, then my conclusion is that I don't really want to build a cluster that can handle this kind of capabilities, because it doesn't. There are two reasons. One is, the reason is that it doesn't really scale that well if you have a completely connected system and you want to have quick access to data. The other reason is that you don't really want this cluster to fail as one standalone unit. If you take the telecom system, you don't really want to have a mobile server that takes care of 50 million users, because if that cluster goes down, that means that 50 million users are out of service. That means big headlines. So just to avoid the headlines, it's a good idea to split the system. And also it becomes a bit more manageable if you have split it up. So the first step then on this grid cluster architecture is, of course, to have a cluster. And the idea I have in mind here is the data nodes here, that I refer to as data nodes here, is nothing else than the NDB nodes that I was talking to you about from MySQL Cluster. So the idea is that I actually use a database server as sort of as a clustered storage engine. And in 5.1 in MySQL Cluster, we have developed support also for storing things on disk. So that means that the client nodes up here, they're using very much already developed technology to get access to the data in the cluster. So then you need to just integrate that as a file system. So that means that most of the components to build this system is already there, which is sort of one of the, in my view, one of the most interesting aspects of open source technology, that you can build on others. You don't have to start digging on your own. You can actually go and fetch something from somebody else that somebody else has developed, and then just continue on that work. The storage controller up there is a new thing, however. The storage controller handles two things. First of all, it handles the problem that I don't want to have everything in one cluster. So that means that there needs to be a way to export all the data in the cluster so that others that want to view a bigger picture than just one cluster can get access to the data. And all those other will get access to the data from the storage controller here. Another aspect of the storage controller is to handle replication. The cluster technology as it is handles replication by more or less do full replication. So you can have a RAID 10 more or less if you think about it as a disk system. So two data nodes here are more or less mirrored. But if you think about the disk system, I mean, and you want to spend money on buying a system with 30 petabytes of disks, then have a fully replicated system, and probably you might even want to have 3 replicas, and then you might want to have another globally replicated system, or even 3 of them. So that means that you might end up with 9 replicas in the end. So it means that these 30 petabytes might eventually end up with 270 petabytes, and that's a big cost. So that means that we need to have replication schemes that are good also on that has sort of less overhead. So that means that we more or less need to apply RAID technologies, but do it on the cluster level instead of doing it on the disk level. So we apply more or less the same technology that we do on the inside the computers, and we apply it on the cluster level. That's the idea, and that's the task of the storage controller. So if I look at the scaling of one cluster, in my opinion, one cluster can scale up to about 100 nodes. That's about as far as it's a good idea to scale, in my opinion. And let's assume that we use something like those Sun server boxes that came around lately with 48 hard disks. That means that one cluster could handle about 750 terabytes. So we're still far away from the petabytes that we're requiring. But it's a fairly decent sized cluster anyway, so we don't have to have like thousands of clusters in order to buy our solution. And to have bigger clusters than this is of course possible to build, but I'm not, there are both the problem that it has, if that cluster fails, that's a very big thing, and also of course the performance goes down when things scale. And then it's obviously so that a big problem in a system like this is that you also want to pump data out of the cluster. So, and here we have assumed that you need to have gigabit Ethernet more or less isn't enough. I mean, you want to have access to more data than what gigabit Ethernet can give you. So you need to have a system that gives you much, much more bandwidth out of the system. And today there are technologies that can give you, say, 700 megabytes per second, but you also have to integrate your application, make sure that the threads, so it's really an intricate thing to write the application such that that the software actually is able to push something like 300 megabytes per second out of the system. So this is sort of interesting work that you have to think a lot about when you think about which threads do what, and how you have to think all the way through the operating system. So my current literature is very much Linux kernel, Mac OS X internals, Windows internals, and things like that to understand how can I integrate the MySQL cluster technology with the operating system, with the cluster interconnect technology, and make sure that I get this kind of throughput. And obviously you get a fairly large cache here as well, but the idea with the cache is not so much to use it it's not so much to use it for the actual disk data. It's more useful to get the pointer to the disk data and also to cache the file information, the attribute information when it was last updated and so forth. And as I mentioned, the data node software is based on the cluster technology. That means the RAID 10. There needs to be some things done with the NDB technology. So that obviously the file storage has requirements that MySQL Cluster at the moment wouldn't support out of the box. So that means that you have to go in and do some stuff there. And in order to get to those 300 megabytes per second, you have to do real-time scheduling, you have to lock memory, you have to lock CPUs, you have to really get the controlled environment. Because if you do a normal operating system with time sharing, I mean, you don't know anything about which threads is doing what, you don't know what happens to cache memories, you don't know what happens to basically to anything. So it's very much about controlling your environment. And NDB is based on research that I did in the 90s, and very much on that research is that you want to avoid using the operating system too much. Basically, you want to build something on top of the operating system. You want to use the operating system, but you want to bypass it more or less. And the interesting thing is that the multi-core technology means that this is more or less possible to do fairly easily. Okay, and you also need extensions to handle cache invalidation protocols. So a file system always have to have a cache. And in order to be able to update things in the file system, you need to be able to invalidate caches. And you can either do that in the software, and then you need to go in and do that in the NDB software. There are some tricks there. There's an interpreter in the NDB that you can actually use for things like that. So you more or less send a message down to the data node and say that, please update this record. And by the way, if you find that somebody else keeps a cache about it, send an invalidation message at the same time. Yeah?
You said before that caching doesn't make much sense because there's no hotspot. So where do you use cache for?
Well, the genealogy application is an example. It would be interesting. I mean, when I'm doing this, I have a little bit broader view than just the genealogy. I agreed on that. For the genealogy, it probably won't make much sense. But if I use it for some other thing, it makes sense. Another way of doing the cache coherency is actually to put it into the hardware, which is something that they're doing in Dolphin, so that you can actually have a cluster with lots of nodes and that you have a cache coherency protocol in the hardware. Another thing which we've been looking at is to get extremely fast failover support. So at the moment, the failover time, when you have a cluster of, say, 60 nodes and one of them fails, it takes the cluster about, if you have a fairly decent operating system, you can probably fail over today in about 1 second or so. But with a multi-core system, with the real-time locking and so forth that I discussed, you can actually get it down to a failover of, say, 10 milliseconds. So that means that you can have an application that can basically do things without noticing. And this would be obviously interesting in some cases, like, for example, on the Wall Street or something like that, where you don't want to miss opportunities. So maybe not in a file system for genealogy, but as I said, and this is just, well, it's more or less a repetition, but this is standard. So then the client node software. So the idea is to integrate the file system in Linux and other operating systems. And there is actually a very good technology for doing that very quickly today called Fuse, file system in user space. It's most likely not the most optimized way of doing it, but it's a very quick way of getting something up and running. So, and given that we have actually a cluster here with tons of computers, it's maybe not the end of the world if each client node spends some extra resources. And it obviously has a protocol towards the data nodes, and it has to handle the file caching protocol. And this is just a display of what happens with the caching protocol. So this is the data node that actually did the update first, and then it discovered that there was a cached copy, and then sent an invalidate message, which got that copy away.
So the data nodes keep track of each and every open file in the system?
Yes. So the data node would have that would be part of the data model that you would do then in the data nodes, that for each open file you would have a description of that, so that you know exactly on which machine that open file is.
Mikael?
Yeah.
Whenever you get a question, can you repeat it?
Oh, sorry. So I've forgotten the question already. So.
Oh, the question was, does the data node then keep track of each and every open file in the system?
Okay, so the question was, does the data node keep track of all the open files in the system? And the idea is that this is part of the data model, so that every record that describes a file also has information about all the users that have this opened at the moment. And it should scale fairly well, since that information is spread on all the nodes in the system.
So I'm curious what the target number of clients to this is.
The target number of clients? Well, I would guess that, given my experience of MySQL Cluster, I would guess that you would have about the same number of client nodes as you have data nodes. Because normally when you have, that's when you get the fairly balance between the CPU power you need on the client nodes and the data nodes. If you use a MySQL server, you probably want to have more MySQL servers than you have data nodes, because the MySQL server has a much higher overhead in that it has to take care of an SQL protocol. But a file server, obviously, is much simpler, so it can go much quicker. The storage controller, as mentioned, has to handle the data node protocol. So essentially, the idea is that the storage controller behaves as if it was a data node. And then it just takes care of that sort of file caching replication I mentioned before. And I mentioned that it needs to be, in order to actually get those really high bandwidth, you need to integrate some cluster interconnect into this one as well. And the way we've been doing in NDB is that we have integrated, it all works with TCP/IP. And so at the moment we're working with cluster interconnects that have socket implementations. And that's very interesting because then we don't have to sort of write specific wrappers and rather put the wrapper in the operating system. So I talked about clusters, and I noticed that the cluster doesn't really scale enough for various reasons. So the idea is now that I simply take those clusters and I create a grid. So the client nodes up here now, they are actually talking to the storage controllers in the cluster nodes. And the client node here can then talk to any cluster. So the client nodes on this level can talk to all the grid clusters in this grid. So that means that it has access to much more data, whereas the client nodes here, they only have access to that particular cluster's data. And you obviously need an interconnect here as well, and then the grid storage controller is there if we want yet one more level of sophistication here. I'm pretty sure that the genealogy system should be able to handle with a grid, but maybe you can come up with a problem that needs one more level. So the scaling here is, let's say that we have about 50 clusters more, so then we should be able to get up to 37 petabytes or something like that. And then the full architecture is when you have, so then on the top level you only have client nodes. So I haven't mentioned the idea with the sort of the grid cluster here is more or less that this is in one site still. So we haven't really dealt with sort of the global part of it. And the idea with the global part is that we have only replication between clusters. So we only have replication on the lowest level in the architecture. So that means that in the cluster here, let's say that this is the slave cluster, or let's say that this is the slave cluster and this is the master cluster. So then whenever something is changed here, there is a signal going from the data nodes up to the replication controller. And then the replication controller sends data over to the slave cluster. And the replication controller here has to make sure that the data is replicated to the other site. And obviously, on the slide, this is a very short one, but it could be the entire globe could be there in between there. So that part is expected to be a wide area network. And obviously, with a cluster of 30 data nodes, and if you have a high bandwidth, high update rate, then obviously you need to have more than one replication controller in the system. And you want to have failover of replication controllers and all that kind of things. And a lot of this is already available in the MySQL Cluster product, but it's most likely so that it needs some tweaking in order to handle this kind of system. So then extensibility. Obviously, you have built your grid storage now, we're saying, and now you want to grow it because customers want to use more. So obviously, you can add disks on data nodes because you can just, either you can plug them in if you have a computer that can handle that, then you can obviously push in new disks and then just type some commands in that makes those disks available to the cluster. Otherwise, you can shut down the machine and start it up again. That's not a problem because that's handled by the data node software. And the same thing with RAM. So it's very easy to add things to a specific machine. And then the idea is that we're also going to be able to add data nodes in the cluster so that you have a cluster up and running, and then you add more data nodes to that cluster. This obviously means that you might want to reorganize the data as well to be spread out in the cluster. Not necessarily, but You want to have that capability at least. And then you can, of course, with this architecture, you can add a new cluster to the grid, or you can add a grid. So I mentioned a little bit about the record format before. So the record format is that there is always data which is locked into memory, sort of. So it's about 50 bytes of memory for each file in this case. And what the in-memory data has a file key. And the idea is that you don't really, when you're searching for data, when you're searching for a file, you obviously have the file name. And the idea is that you make a hash on the file name, and then you use the file name as the hashed file name, you use that as the primary key. That obviously means that you have to have some resolution if there's two file names that hash to the same value, but so that needs to be part of the file key as well. But the actual file name is stored in the file attribute information, so that's the idea. And then the interesting thing here is that in NDB you can store things in disk-based if you like, but you can just as well create a table where this information is stored in memory. So if you want to create a file system that's locked to memory, it's very easy. I mean, it's just a different command, and then all of a sudden you have a main memory file system which is clustered. And you can decide that file attribute information is in main memory, but that the disks, the data is on disk. So it's very flexible in that way. And I don't think there's anything particularly new on this slide. Snapshot handling, well, that's when you deal with file systems, there are lots of things that are new that doesn't exist, that you don't have as normal requirements in databases. So the one thing to think about is, of course, that the data nodes needs to be stacked with lots of disks. But most of the controllers, storage controllers, they don't really need that much disk, if they need anything, if they need disks at all. So it means that you need to have a number of computers. So the major technical issues. Obviously, if you have a system this kind of big, its manageability is a very big issue. So most of the work that I'm thinking about right now is sort of, how do you make it easy to manage a big cluster? How do you make it easy to upgrade it? So, I mean, just think about upgrading a system with, well, I guess you have tried that out. And so it's a big issue, obviously, that one has to think about. Easy upgradability. Data flow, I mentioned that a couple of times already. I mean, you want to really have a data flow going. So not only do you have to get the data flow going inside the machine, but you also have to get the data flow going within the cluster. So there's a lot of dimensioning here. You have to actually, before you put the system into place, you have to do dimensioning. So coming from the telecom world, that's not new to me. I mean, whenever you put a telecom system into place, you always do dimensioning of the system before you put it into place. And I presume it's not new to you either, or at least not to all of you. Shouldn't be new. Response time. To get response time down means that you need to tightly integrate it and the cache invalidation protocol. And then other interesting applications, emails, like Gmail, shared disk for databases. That's one of the reasons why I also think a lot about the update stuff that for genealogy application obviously isn't interesting, but if you use this file system, for example, to run an Oracle or something like that, then obviously you want to think about things like that. And these are pretty obvious places to put clustered file system as well. So I think there is some time for more free questions, either on this or if you want to have questions on MySQL Cluster as such.
People ask
Oh, I always forget that. So the question was, have people asked for NFS interfaces to the system? And it's if you integrate it into the Linux operating system, it kind of becomes an NFS automatically without using NFS. But obviously, using NFS could be interesting as well. But in essence, if you integrate it into the operating system, it is a networked file system by default. So you don't really get much benefits. And you can actually view the storage controller in a sense, is in a sense an NFS, similar to an NFS server. And NFS has lots of problems. So you obviously have it out there in the industry, so I'm pretty sure that if we put something, that there will obviously be places where NFS will be used anyways, but it has many drawbacks when it comes to reliability. So failover and things like that with NFS is not really great. You can get locking, you can get file locks that stay around even after crashes and things like that in NFS. So. Yeah.
Other than the telecoms companies, are there other companies which are using MySQL Cluster?
So the question is, other than the telecom customers, are there other people using MySQL Cluster? And one other area which is fairly common to use MySQL Cluster is in session management for web servers. So obviously, when you go to a site and you have, for example, you're buying things, for example, and you put something into a session, and you want to be able to come back to that. That's a very popular place to put MySQL Cluster in. And there are a couple of others as well. But these are the two most popular variants at the moment. And then there are lots of others that sort of don't come up immediately in my head. But
so I think that I have a question here. So it took you quite a while to build the NDB in the first place, right? So when are you finished with this?
Well, I'm retiring in 14 years, so before that at least.
Okay.
So I mean, you could view this a little bit as a vision. So it's not a done deal or anything like that. But I like to work with visions. So when I did the NDB Cluster, I did a Ph.D., as Jonas mentioned, in 1998. And it's 8 years later now, and it's now in operation in all kinds of places. I think it will go faster with this one because I'm not building from scratch this time, so I have lots more technology to start from. But it's obviously not going to be a complete done deal next year.
Right. Yeah, as it turns out, his PhD thesis is quite interesting reading because essentially this designs the whole architecture for NDB cluster and goes very much into details about storage and everything. So a lot of things have been thought out in advance for him.
Yeah.
Right?
Yeah, it's not. Yeah, I've been thinking about those problems since the 90s. So.
Any more questions?
Do you have any actual numbers for performance, like read-write performance on these clusters?
On these clusters or on MySQL Cluster?
Well, either. I mean.
Well, we have been doing. In 2002, for example, we did a test with MySQL Cluster, NDB Cluster as it was at that time. And this was with UltraSpark 900 megahertz CPUs. And then we managed with a 32-node cluster to get up to 1.5 million reads per second and 300,000 updates per second. On my local sort of dual core machine, running 2 data nodes, 1 client node, I'm able to run 110,000 reads per second and about 70,000 replicated updates per second. So these are very small updates and reads then, so it's not like kilobytes.
Right. So do you have any numbers performance? Because using some machines, which means that using SCSI, basically SCSI disks and some hardware. Have you tried it on different platforms?
Yeah, we have tried it. Oh, sorry, the repeating of the question. Can you repeat it? You're probably a better memory than me. So the question was if we have tried it on other hardware than some hardware with SCSI disks, and yes, very, very much so. We've tried it with both SATA disk and with all kinds of pieces. I mean, it's very well used over the globe, so I'm pretty sure we have tried more or less everything that's potentially possible. And what you for MySQL Cluster is really bandwidth to the disk. We don't really do very much sort of random access. In the main memory variant, it's all sequential. It's all writing. And the actual thing, what we have managed to do with the architecture when we have added disk data, is actually that whenever you do an update or an insert, you more or less write sequentially still. So we have very much a sequential writing to the disk. So that means that it's not that important to have a very fast. Obviously, when you do random access of disks and so forth, of smaller items, then obviously the disk will. But in a file system, most of the data is actually fairly large. So I don't really see any major benefits with the SCSI disks. SATA disks will play out fairly well as well in most cases.
Is the main advantage of your new software over MySQL, like clustering in MySQL, is the main advantage just the grid, like grouping together clusters in grids, and then like further clustering on top of that? Is that the main advantage, or what would you say is the main advantage of this? Like it sounds like, I mean, you're creating some new open source software. Why do you need to create that? Why not just building into MySQL?
Well, first of all, repeating the question. So the question was, what sort of is the benefit of this technology? Is it the grid thing or why not just build this into MySQL as such? Well, the first thing is with MySQL as such is that it's a database technology. So whereas this is something completely different, or not completely different, but it's a database, it's a file system. And in many aspects, I mean, I'm building upon MySQL technology here. So it's not like that I'm inventing. Those parts that comes from MySQL that fits into the picture will be reused, of course. So it's not the idea that I will rewrite anything of that. I mean, it's open source, so I can reuse that. The grid thing is obviously a new thing. That's a completely new idea that hasn't been in MySQL before and hasn't been in database technology. I mean, Oracle calls their 10th version Oracle Grid, but it's really just a cluster. But I'm pretty sure that Oracle has this kind of technology in the works as well. So this is actually where I think that the cluster technology this is the sort of the path that cluster technology, both in file systems and in databases, is going. So I think that's a major contribution. And then another thing which, I mean, I'm pretty sure that the performance of this thing and the high availability is another thing that is, I mean, if you look at the clustered file systems that are available out there, it's very few of them that give you high availability as an open source technology. Do
you have any more questions? Okay, thanks for coming, and catch us again on Google Video.
Thank you.